Welcome back to the Deep Dive. Today we are jumping into what might be the single most important transformation in the history of the universe.
It really is. We're talking about how the cosmos went from being, well, a pretty boring soup of basic gas
Right.
to an environment that's actually rich with all the elements you need to build, interesting things.
And we're going to call this era the Cosmic Dawn. This is that critical period, about 50 million to a billion years after the Big Bang?
That's the one. It's the moment that finally ended the cosmic dark ages.
Flip the light switch on.
Exactly. And the sources we're looking at today point to one main culprit, or maybe hero, for this transformation.
Not galaxies, not black holes, not at first anyway.
Not at first. The primary engines, the real drivers, were the very first stars. And we've now got some incredible direct evidence from the James Webb Space Telescope, the JWST, that shows us exactly how they did it.
Okay, so let's start there, because when we say stars, we have to be super clear. These are not like our sun, not even close.
Not at all. These first stars, what astronomers call population 3 stars, well, they were true monsters.
And they were built differently from the ground up.
Completely. They were made of literally nothing but hydrogen and helium.
The stuff came straight from the Big Bang.
The absolute pristine original ingredients. And that lack of anything heavier, it completely changed how they formed and how they lived their lives.
And it's that lack of heavy stuff. I mean, things like carbon, oxygen, iron, that's the reason they got so unbelievably huge, right?
It is. It all comes down to physics.
Yeah.
In a modern gas cloud, those heavier elements act like radiators. They let the cloud cool down really efficiently.
Which lets it break up into smaller pieces.
Exactly. It fragments, and you get lots of smaller stars, like our sun. But these early clouds, they didn't have those radiators.
So they couldn't cool off.
They really struggled to, so the cloud had to gather a just monumental amount of gas before gravity could finally win and, kickstart fusion.
Which is how you end up with these giants that are 1,000 to 10,000 times the mass of our sun.
Colossal and burning incredibly hot and fast.
So they live fast, die young. And in that short, explosive life, they do three things that basically build the universe as we know it.
That's the framework. First, they cook up new elements. Second, they die and spread those elements everywhere.
And third, they start clearing out the cosmic fog.
And that's why they were so critical. They weren't just big. They were the universe's first architects.
I love that. Architects. Okay, so let's get to that first role. Chemical alchemy. The sources use this great analogy. They call these stars the universe's first chefs.
It's a perfect visual, isn't it? The early universe had this primordial pantry with just 2 ingredients.
Hydrogen and helium.
And that's it. These monster stars were the cosmic pressure cookers that took those basic ingredients and, under insane heat and pressure, started making something new.
Okay, so what's the first thing on the menu? What were they cooking?
Well, this is where it gets really interesting, and it's a key find in the research. The evidence suggests they were incredibly good at producing large amounts of nitrogen.
Nitrogen. That's specific. Why is that so important?
Yeah.
I mean, they're making other things too, right? Carbon, oxygen.
Oh, absolutely. But nitrogen is foundational. Think about how modern stars work. A lot of them rely on what's called the CNO, cycle carbon, nitrogen, oxygen, to burn fuel efficiently.
It's a catalyst.
It's the catalyst. So finding so much nitrogen so early on tells us these first chefs weren't just throwing random ingredients in the pot. They were preloading the universe with the exact chemical tool needed for the next generation of stars to form and burn better.
So they're not just seasoning the soup, they're providing the spark plug for all future star formation.
That's a great way to put it. But, cooking is one thing. If all those new elements just stay locked inside the star, it doesn't do anyone any good.
Which brings us to their second role, the delivery service.
Yes, dissemination, or what the sources call chemical seeding.
The ultimate dispersal.
Because these stars were so massive, they didn't just flicker out. They died in unbelievably violent supernova explosions. And those explosions blasted all those new elements, the nitrogen, the carbon, everything, out into the space around them. That's the seeding.
And that seasoning creates the chemical fingerprint that gets baked into the next stars, the next galaxies, and eventually planets like ours.
This isn't just theory anymore. This is the really exciting part. We now have concrete proof.
This is where the JWST comes in with a record-breaking discovery. They found the single earliest supernova we've ever seen, right in the heart of this cosmic dawn.
It is just a spectacular find. JWST spotted a supernova linked to a gamma ray burst. They call it GRB 250314A. This thing went off when the universe was only 730 million years old.
Just stop and think about that. That's only about 5% of the universe's current age. It's incredible. It completely smashes the old record by, what, over 1 billion years.
It does, and finding it was this amazing rapid response effort from teams all over the world.
The first alert came on March 14th from the SVOM mission.
Right, a Franco-Chinese satellite. Then NASA's Swift Observatory jumped on it, found the X-ray source. Just hours later, the Very Large Telescope in Chile got a redshift.
And that's what confirmed the distance. A redshift of 7.3, meaning we're looking back 13 billion years in time.
And because it was a long gamma ray burst, it lasted about 10 seconds. That was the immediate clue that we were watching a massive star die.
The coordination is amazing, but there's a really cool twist in the physics here that the scientists actually used to their advantage.
Yes, the anomaly.
A supernova nearby. It brightens over a couple of weeks, right?
Yeah.
But this one took months.
And that is a perfect, real-world example of cosmological time dilation.
Because the universe is expanding.
Exactly. The light from that explosion traveled for 13 billion years to reach us, and the whole time, space itself was stretching. That stretching doesn't just stretch the light, that's redshift. It stretches the event itself.
I love the analogy they use. It's like watching a video of a runner, but someone is physically stretching the film out as it plays.
So the runner just appears to be moving in slow motion.
So the star really exploded over a few weeks. But from our perspective, the whole event looks like it's happening in a crawl.
And the brilliant part is, the researchers could predict this. Based on that redshift, they calculated that the supernova would hit its peak brightness about 3.5 months after the initial gamma ray burst.
That's incredible. So they didn't just point JWST at it right away.
No, they waited. They scheduled their observation for July 1st to catch it right at its brightest. It was this beautiful piece of strategic science.
And by doing that, they proved that Webb can find the light of a single individual star at a time when the universe was barely a toddler.
It's a game changer.
Okay, so we've got the cooking of elements, and we've got the dispersal via supernova. What about that third role? The big structural changes these stars cause.
That would be cosmic reionization. This is how the universe became transparent. Before these stars turned on, the cosmos was filled with this thick, opaque fog of neutral hydrogen gas.
Light just couldn't travel far.
It couldn't. But the sheer amount of ultraviolet light pouring out of these monster stars was powerful enough to start stripping electrons off those hydrogen atoms.
Ionizing them.
Right. And that process is what cleared the fog, allowing light to travel freely across the universe for the first time. It's what let the first large-scale structures, like galaxy clusters, begin to form.
It's the final transition into the universe we recognize. But the source material points out something really weird about this particular supernova, GRB 250314A.
Yeah, the paradox. When they looked at the data, the explosion looked, and the quote is, shockingly similar to a modern nearby supernova.
Which is strange. I mean, we've just spent all this time talking about how different the ingredients were. How can the result be the same?
It's a fantastic question. It suggests that the basic physics engine of a core collapse supernova is incredibly robust. It works the same way whether the star is made of pristine gas or recycled star stuff full of heavy metals.
But the researchers think there's more to it.
They do. They're careful to add that while the overall light curve looked similar, they fully expect that when they dig into the detailed spectra, the actual chemical fingerprint of the light, they'll find the differences.
The signs of that much lower abundance of heavy elements.
Exactly. You'll see the nitrogen, but you won't see the iron and the other stuff that a modern star would have. That's the smoking gun they're still looking for.
And JWST managed to do one more thing, didn't it? It saw the home galaxy.
It did. It detected the very faint, very red host galaxy where this star lived and died. And it looks pretty similar to other galaxies from that era. The next step is to use future gamma ray bursts as cosmic flashlights.
How does that work?
The afterglow from the burst shines through its own host galaxy. And by looking at what light gets absorbed, you get a much clearer chemical reading of that galaxy than you ever could from its own faint light.
That's brilliant. Okay, so to sum this all up for you listening, these first massive stars were the universe's architects. They were cosmic chefs cooking up new elements like nitrogen.
Then they died in these massive supernova explosions like GRB 250314A and seeded the cosmos with those new ingredients.
And finally, their intense light cleared out the primordial fog in an event called cosmic reionization, which let the universe as we know it start to take shape. They turned simplicity into complexity.
Which leaves us with a final provocative thought for you to take away.
Go on.
If we can see a star explode just 730 million years after the Big Bang, and the explosion looks shockingly similar to one happening in our own galactic neighborhood today, what does that tell us about how fast the universe figures things out?
It's a really good question. It implies that the fundamental rules of physics, the ones that govern how stars die, must have been established and perfected almost instantly on a cosmic timescale.
Even though the universe started with almost nothing in its pantry, it somehow learned the recipe for a spectacular stellar explosion right away. The efficiency of it all is just staggering.
There's always more to learn about the cosmic chefs and their first meals.
But for now, that was a deep, deep dive.
We'll catch you on the next deep dive.